So it's my pleasure to introduce Professor Peter Abil. Abil did his PhD at Stanford, and he showed very impressive results in apprenticeship learning with helicopter maneuvers that can only be executed by expert humans. And after that, in 2008, he joined directly UC Berkeley as a professor, where he has been pioneering the research in deep learning for robotics, imitation learning, unsupervised learning, safe AI, and he has received a number of awards, like the Early Career Presidential Award by Obama last year, or the 35 under 35 innovators by MIT, and more recently he has been a research scientist at OpenAI, and now he thinks that this field is moving fast enough to actually start a startup, Body AI. And now he's going to be talking today about hierarchical reinforcement learning. So please welcome Peter Abil.
Hi everyone, really excited there's a hierarchical reinforcement learning workshop because I've actually struggled a lot with hierarchical reinforcement learning, and I think I'm going to be able to learn a lot here, I hope so. I've actually struggled a lot, but nevertheless I've continued to try to work in hierarchical reinforcement learning because I think there's a lot of reason we need to work in HRL, even if the progress, at least for me, has felt really slow. So why do we need hierarchy? Well, if we have a robot that does the chores at home, maybe it only has 10 chores a day, so that's 10 time steps. But then, if it needs for every chore, go through 100 steps to do the chore, now you have 1,000 time steps in the robot's day, and maybe it picks up an object, places it somewhere, goes somewhere else, and so forth. But now, to do that, they might need to plan individual footsteps, and it might be many of them for any time you want to go somewhere. So now maybe there's 100,000 time steps in a day of the robot. And then, if you start thinking about sending controls to each of the individual motors of the robot, all of a sudden you end up with 10 million time steps in the day of the robot. And 10 million time steps in a single episode is well beyond what we're able to do with current reinforcement learning techniques, including the most advanced hierarchical reinforcement learning techniques. So there's a lot of work ahead of ourselves. And so actually in 2015 is when I started to spend a lot of time on hierarchical reinforcement learning. At the time, mostly together with John Schulman and Rocky Dwan. And we looked at a lot of things, and I thought maybe I'd summarize some of the things we looked at, even though we did not make any progress ourselves on these. So one thing we thought was super promising, and we still think, is feudal reinforcement learning. Came out in 1993. There's not a lot of follow-up work on it, actually, since 1993. The key idea here was that instead of having sometimes one agent, you have a manager at the top, and the manager can deploy an agent below it, which can in turn deploy an agent below it, and this can repeat as many times as you like. And each agent receives instructions from the agent above it, which is a description of a task, and gets rewards from the agent above it, and then executes by giving instructions to the agent below, until you reach the bottom level. And so this just seemed very much the way humans set up organizations, where at the top people tell the people below what to do, and give them some KPIs, some key performance indicators, what you're supposed to achieve, and then if you do that, hopefully the whole organization works. So it seems very natural. The experiments in the paper were grid worlds, and didn't end up going beyond that, and we couldn't really figure out how to generalize it at the time. Turns out, 24 years after the original paper, 2017, Alex Veshnevitz at DeepMind with several collaborators managed to expand on the feudal networks with the feudal learning with feudal networks. And this architecture is essentially the one from the feudal learning paper, but now there's just one manager instead of many manager hierarchies, so just one manager at the top, one worker, and them working together allows to learn over longer horizons more readily than we could without this kind of architecture. What's really intriguing here, I think, is the transition policy gradient idea. So the worker does what you expect it would do. It tries to optimize the reward with a standard policy gradient type method against whatever it was tasked to do by the manager. And also a little bit based on the real reward in the world. But now the manager, actually, its gradient, policy gradient, is based on how much reward was achieved relative to average, the advantage achieved from that time step onwards. And then this here is a new type of policy gradient which says The manager will change how it's doing goal setting based on how well, if things were good, then whatever happened, change in state happened, the manager should start setting goals that are more similar to the change in state that just happened. And that's really the key difference in the algorithm here, to make it not end-to-end from the bottom reward to the top, and allow them to make a really nice progress on this problem. Still, only one layer. One worker, one manager. The original feudal learning had in mind that there would be many, many managers on top of each other, and that this would help. And that's still a completely open problem to make that happen. Another direction we looked at a lot was option learning. In options, you have a system where instead of having a manager, you actually have some kind of master policy at the top. And the master policy will choose an option that is a sub-policy to execute. And that sub-policy can on its own decide when it's going to exit, when it feels like it's done enough, and then the master can choose the next thing to do. And recently there's been some nice derivations there on how to make that end-to-end trainable with the option critic. Again, still only 2 levels in the hierarchy, and I think what we really want ultimately is something where we might have 10, 15 levels in the hierarchy, not just 2. So I'm just highlighting this here, and that yes, progress has been made, but I think there's a lot of thought that still needs to go into potentially extending these routes to get much further. What we actually spent a lot of time thinking about was the information theoretic approaches. The idea in the information theoretic approaches is something along the lines of, if you set a goal now, whatever goal you set now as a top level agent should tell you something about what happens in the future. If that's true, then that top level agent was a goal setting agent, and it means you were doing something hierarchical. And so if you're doing something hierarchical, then maybe you'll hope that things will work better because, well, hierarchy will make things work better. We tried a lot of different information theory criteria, including ones that were in here and other things we tried. We tried it on this world here, which we thought was a good test environment. So you're dropped in a grid world, and to move, you can't just choose north, east, south, west, but you have to choose a passcode, but you don't know which are the passcodes in that world. So the low-level agent would need to discover that 220, a sequence of 3 low-level actions would make you move east. And if it discovers that, then hopefully the high-level policy would reuse that low-level thing, low-level sub-policy to navigate mazes more effectively. Still think it's a very good world to test things in. But I'll say, I don't have much more to say because we tried for about a half year to get things working better than what people had done before, and we didn't succeed. So, but I still think all of these directions are quite exciting and interesting to push forward. Just new ideas are needed and what we were able to come up with. At that point, actually, we switched gears a little bit. We said, why are we even doing HRL? We want hierarchy. We've seen 3 different ways of trying to achieve hierarchy, but we're not able to really improve results with it compared to what's already in the literature. And what's in the literature is not the hierarchy we dream of with many, many levels and solving 10 million time-step problems. It was still quite limited. So we said, why do we even care? One is credit assignment. If you have hierarchy and you have only 10 time steps, because you're reason at the high level, credit assignment is much easier than if you have 10 million time steps. So you might do faster learning within your one environment thanks to the hierarchy. Another reason would be exploration. If you have primitives that you use to explore with, you might do things more consistently and hence explore parts of the world you otherwise, with random walks, would maybe never get to or would be taking exponentially long. Another one is that you might want to improve your generalization capabilities in terms of transferring to new tasks. So maybe hierarchy is such that if you train in one environment, you acquire some skills in that one environment, and maybe it's not even possible, maybe it is, maybe it's not. Maybe it is possible, maybe not, to learn more quickly in one environment thanks to hierarchy, but definitely should be possible after you train in one environment to extract primitives that should help you to train more quickly in another environment. And that's what we started focusing on at that point. And I'll tell a little more about what we've done that ties more directly into this last bullet point here. So it's hierarchy in the sense of faster transfer, rather than necessarily being in one environment and hoping that we'll learn faster. Not saying that we shouldn't hope for that, but don't have much to say about that yet. So the first line of work in this direction that we looked at is stochastic neural nets for HRL. It is the following. Often in robotics, what happens is that you have a robot, And you can train it for a long time if you want, in your lab or in an environment where the robot is currently set up. But then what you really want is that it adapts quickly to new environments in the future. But you don't have time to train it there. You're going to deploy it there, but you can't directly train it there. And so the question you could ask is, can we set up something where you train in the lab some basic skills such that later you can learn more quickly in other environments? So this is also very closely related to recent work by Nicholas Hess and collaborators at DeepMind. So the overall idea here is that you would pre-train for some tasks to learn skills that are relevant for the future, that make you sample efficient in the future, as well as for acquiring the initial skills, and hopefully you acquire a diverse set of skills, so you can use that in a wide range of future challenges. And then maybe put a hierarchical structure on top that has a manager network that chooses between the skills when in a new environment. So, to learn the relevant skills, we define a proxy reward function. For robots that do locomotion, this is actually pretty easy to do by hand, because where the center of mass is of that robot is a really good proxy reward for whether you're achieving things. It's about getting somewhere, and in that way you ignore all the details of the joint angles. The reward is just about where the center of mass is of the robot. Then, if we just reward the robot for, let's say, changing the coordinates of the center of mass, we might get something like this over multiple runs. So we can do multiple runs, they'll find different local optima, and that will give us different sub-policies we can use in the future when deployed in a bigger new environment. But that's kind of sample inefficient because we're doing 6 independent trainings, and if you train independently, then maybe you train the same thing over and over, and now that's a waste of time. There's no parameter sharing between the primitives. That's not great. So we actually changed that into a stochastic neural net that's shared across all of them. And there's also no explicit control if you just do independent runs over the diversity that you get. So we looked at explicitly introducing information theoretic criteria to introduce diversity. So we have a mutual information bonus between, well, I'll say a little more about that in a moment, once it's on the slide. So stochastic neural nets, once we design, take in a one-hot encoding that you sample. That one-hot encoding then hopefully is associated with a skill. Each different encoding has a different skill. It's multiplicatively interacting with the other inputs. We found that that gives it more strength in terms of affecting what happens. Doing that, it's possible to then have multimodal policies that you learn at the lowest level in your pre-training, which you can reuse later when doing training of the master policy in a new environment. The mutual information idea is very related to the InfoGAN idea, which was presented last year at NIPS. The idea here is that you want this somehow, it to be the case that after your robot has acted based on one hot encoding input, has acted according to that for a while, and you see what the resulting trajectory is, you should be able to recover from that what the input encoding was. If you can do that, then there is high mutual information between the input encoding and the behavior you get out. Then, if you want high mutual information overall, then what you also need is that you have a high entropy over input encodings you use, and then corresponding to that, you'll get high entropy over behaviors you get. So here are a set of behaviors that you can get, and the more you can crank up this coefficient more to get more variation in behavior, as you see all the way on the right. And once you've done the pre-training, you can train a manager network on top of these pre-trained skills to hopefully solve new tasks. These management networks are able to explore much more quickly than you could with standard exploration at the low level. What you see on the left is low-level exploration, just random noise. On the right, you see the diversity of trajectories when using a management network on top of a pre-trained set of low-level skills. We test this in a few canonical long-horizon environments where learning from scratch is very difficult. One is maze navigation, another one is the food gather environment. I'll show you the results for maze navigation. The paper has the results for food gather also. So what you see here is that the learning curve, based on these primitives, is a lot better than if you don't pre-train with primitives. And let's watch a movie here of this in action. So what we see here is this snake robot supposed to navigate to the other side. It's using one-hot encoding corresponding to the first latent mode initially to move forward. Now I switched to mode 5 because it has to make a 90 degrees turn. Switches to mode 3, it's going diagonally. And so you see that over time, this is the fully trained master policy. It's switching between these latent modes in a way that it can get to the target location very quickly. What we didn't watch here is the learning, but also thanks to having these primitives, the learning can proceed a lot more quickly than it can without those basic modes. Another thing we switched to at the time was thinking that maybe if we are not getting what we want, at least not in our attempts, out of just imposing information theoretic criteria to impose a hierarchy, just directly end-to-end train for what we want out of the hierarchy. End-to-end train for fast generalization in new environments. So what does that mean? We would want an agent that is such that if it's deployed in a random environment M and gets a set of trajectories, capital K can execute, that it collects high reward. If it does that, that doesn't mean it's necessarily a hierarchical agent, but it means that it has some properties that we also hope to get from hierarchical agents, which is that you discover some kind of basic primitives that you might be able to reuse when dropped in a new environment. So you get dropped in one environment, the next one, this repeats over and over. You have a training objective to be an agent that's good over a wide range of environments. So what we're learning here is not a policy. What we learn is a reinforcement learning agent that is good at adapting to new environments, and hopefully that agent is really good at adapting to many, many environments, hence having some notion of hierarchy in it. So one way you can do this is put a recurrent neural net as the agent. That's a generic computation architecture. Then different weights would correspond to a different algorithm inside the agent, as well as a different prior over environments it might encounter. Different activations would correspond to a different current policy it thinks it's the right policy for this current environment. The objective itself is actually a reinforcement learning objective. You're trying to train something that acts well when dropped in random environments, and so we can bootstrap off of standard slow reinforcement learning algorithms. In this case, we used proximal policy optimization as our slow reinforcement learning algorithm that trains up the fast RL agent that hopefully generalizes well to new environments. So for example, at training time, you're faced with bandit problems. At this time, you get faced with a new bandit problem. The properties of the bandits you're faced with are different. You don't know the probability of payoff, but you hopefully train up an agent that knows how to explore quickly, understands what you need to do in this new kind of environment. So we compared this with base optimal algorithms designed by humans, such as the Gittins in these algorithms, and we see that in this case, RL squared, the learning to reinforcement learn, can do as well on small, medium, and medium-large bandit problems as the Gittins indices. Here's another example. Here the distribution over environments is, it's always going to be a cheetah robot. But what's different in each environment is the reward function. The reward is related to speed of locomotion. So maybe it's reward for the faster you go to the right, the better, the faster you go to the left, the better, or maybe it's a very specific speed that you're supposed to match. And so as your agent gets dropped to control this cheetah robot, and it's in a test environment, the hope is that it would wiggle around a little bit, get reward based on what it did, probably not very high, but then realize, oh, I got low reward and I did this, that probably means I should do this other thing, and immediately adapt to what it needs to do in this new environment. And in fact, this is what we're watching here. We're watching the very first episode of this agent deployed in a sequence of tasks here. So running backwards is currently the task, now running at speed 0, now running at speed 0.5, and this is the very first episode, the very beginning of the first episode that we're watching. It immediately maximizes reward for the current task. Same can be done with Ant Robot, and the same kind of results. It, within the first few time steps, is able to maximize reward on this task. Here's a even more challenging one, vision-based navigation. So the agent can steer 2 degrees to the right, 2 degrees to the left, or go straight forward. It gets in monocular camera images. It doesn't have the map. So it gets trained up in a wide range of environments where it gets dropped and is supposed to solve this problem, and then it gets dropped in a new testing environment, and hopefully it's good at understanding what it means to navigate a maze. Randomly moving around is what you see here. It doesn't really get you much. A trained agent with RL squared will give you this. And this is exactly what you would hope for. This agent efficiently navigates hallways. It doesn't have the map, so it cannot just shortcut to the target, but it navigates efficiently, explores, then sees the target, goes to it, gets dropped in that same environment again, remembers from the past its hidden units, having the activations, information from the past navigation to now succeed in its new task. After these results, we started kind of circling back a little bit more explicitly to hierarchy itself, temporal hierarchy explicitly. So what we set up is an architecture that is a little bit like the option critic, but not the exact same training algorithm, and it's also not exactly the same architecture. So what we have here is a master policy that gets to choose a master action, which means which of these sub-policies currently gets passed on to execute its chosen action. The master action will be chosen every, let's say, 20 or 100 time steps, so it acts at a slow time scale, which allows it to do that kind of credit assignment that we hope for over longer time scales, because it only takes a few time steps for the master, even though at the low level it's many, many time steps. And then the low level policy acts at the full rate of control that we have access to. And the goal here is that we set up an end-to-end optimization problem that finds sub-policies that enable the learning of the master policy. So we're not trying to train this as one thing. So we're not training it as both training theta and phi 1 and phi 2. Instead, what we're training is we're only training phi. We're trying to find sub-policies, phi 1, phi 2, phi 3, such that if you randomly initialize the master policy with some initial theta 0, and then you run an RL agent that's initialized that way, and that has access to these sub-policies, then that RL agent should do well when dropped in a random new environment for a certain number of episodes. So we're explicitly trying to discover sub-policies that are good to learn from. This is a little different from a lot of other work in hierarchical RL, where the goal is to jointly train theta and phi 1, phi 2, phi 3, and so forth to be good in the current set of environments. Here we're specifically trying to discover sub-policies that are good for learning on top of it in new environments in the future. Actually then we can revisit the bandit problem. Now it's called the moving bandit problem, meaning that the blue bandit is in the first episode over here, but in the second episode the blue bandit's over here, and it'll keep moving around. And so what you'd hope would happen is that in this kind of bandit problem that you learn sub-policies corresponding to I should move to blue bandit or I should move to green bandit. Then when dropped in a new bandit environment, where the pairs of green and blue have changed, you'd still be able to reuse the sub-policies of moving to specific bandits, and that master policy would then get retrained to learn what bandit it wants to pull and make the sub-policies go there. And this is actually what emerges. So what we see here is that sub-policy 1 learns to go to blue bandit, sub-policy 2 to the green bandit. Here's another example. Let's say we want an ant to navigate mazes. And there could be a wide variety of mazes, so we're not trying to have the ant solve one particular maze in this setting. We're trying to have the ant develop a set of sub-policies such that if it has access to those sub-policies, a master policy on top of that, in our case trained with proximal policy optimization again, if we train a master policy with proximal policy optimization on top of those sub-policies, then that master policy will be able to explore that new environment quickly and learn a policy that achieves high reward in the new environment. And indeed, we see here that this kind of training allows you to discover 3 gates. Why these 3 gates in the set of environments that we trained it in? Because the goal was always off to the right. And so what it discovered is that what you want to do is moving straight to the right, moving diagonally up to the right, diagonally down to the right, and if you compose those 3 policies, you get short paths to the goal. And exploring among those policies is what gives you fast exploration in these kinds of mazes. Thank you. So I think there's a question that's already on my slides here.
Yeah, so this is the experiment. We're gonna have a challenger ask like an extended question. So the first challenger is Danishar Hafner. He's a graduate student at UC London and part-time also at Google Brain. So, go on.
Hello everyone. Thanks Peter for the great talk. So, with the previous architecture, meta learning shared hierarchies. The manager gets updated every fixed number of time steps. And so for some tasks, timing might be critical. Let's say you want to jump over some obstacle, or you want to pick up a passenger and you don't want to wait at the destination until your manager takes the next time. So my question is, how do we bring timescales and temporal abstraction into these into these controller hierarchies? Should the manager or the skill predict when the skill is over, or should we maybe not focus on fixed timescales, but have more like a modulation signal that's moving at every time step, but it's moving slowly, so there is some temporal abstraction? Or should we maybe sidestep this problem altogether and just learn temporally abstract features and a single policy conditioned on that?
Thank you, Danitar. Really good question. So let's see. I think this question is also highlighting that I think different people are trying very different things for this. I think it's undeniable that you need to adapt your time scale. You cannot just say 100 time steps is the right thing for everything. But then how to actually resolve it, I think there's quite a few open problems there. So maybe I'll just kind of highlight how the different existing approaches go about this. But I don't think there's one that's necessarily the clear-cut solution. So if you look at the feudal networks, there's some kind of dilated LSTM running at the top at a fixed timescale that's different from the low-level timescale, but at the same time, that LSTM is set up to actually have, I believe, 10 or maybe 100 LSTMs run in parallel to each other, and so each one, at any given time, one of them is active and can influence what the lower level is asked to do. So it gives you some flexibility to change what the goal is right now, but not maximal flexibility, because most of the LSTMs are quiet at any given time, but it also then imposes some kind of temporal scale on it. The classical options tend to decide themselves when they exit, so they decide when they reach a state that they're exiting that particular option, and it's a termination condition, which can be stochastic. Then what I showed here with the meta-learning shared hierarchies is on a fixed clock. There's no reason that needs to be on a fixed clock, per se. I'm quite sure that you could retrain the master later to use a non-fixed clock, or even at training time have to use a non-fixed clock. We haven't tried it. I suspect it would work better in tasks where this is relevant, but for locomotion, it wasn't too relevant to do that. I think there are other approaches that I haven't highlighted here that are quite interesting. For example, STRAW, I forgot what it stands for, but essentially STRAW is an approach where you are constantly making a new full plan. So you have a full plan that your recurrent neural net outputs, and at any given time step, you refine that plan. You write over the sketch of the plan, a new plan. And so you're constantly at the master level updating a longer horizon plan, but you're doing it based on what you already had before. So again, you're making a small change to your previous plan, and that maybe is enough to kind of re-steer yourself onto something new. Yeah, I think overall it's a very good question. Maybe one counterpart to the need for this would be if we really had, let's say, 20 levels in the hierarchy, it might be okay to just have binary. So the lowest level goes like 2 steps compared to the level above, and this kind of keeps going by a factor 2, and maybe that could be already pretty close to what we need without needing very adaptive adjustment of when things end.
Yeah, thank you very much, Peter, for willing to take this challenge. These extended questions bring maybe a little bit more depth to the answers also, so thank you. We still have time for a couple of audience questions, so if you want to just walk up to that mic.
In the example that you showed, did you fix the number of like ends to have like 3 or 4 or n number of options to be learned, or you just kept it open?
So for this setting here, we specifically gave it 3 modes. We also tried with more than 3. It did not do anything meaningful with the others. Maybe because the problem isn't rich enough, or maybe because there wasn't enough learning signal to discover this, and maybe, I mean, learning signal of course relates to details of the architecture also, whether the architecture allows you to propagate signal and so forth. So we found 3 was good and more than 3 didn't help in this particular environment. We also did some experiments with the humanoid. In the humanoid environment, you'd imagine that you could discover many, many different gates. So we discovered running and we discovered crawling. But then giving it more modes for now did not lead to, let's say, I don't know, cartwheels or anything like that, which in principle you would hope for. I think what we need in this kind of training, because this end-to-end training of the sub-policies, I think what we need environments where the different modes are useful when the sub-policies are being trained, such that there is a reason to discover them. And so the reason for the humanoid crawling was discovered is because part of the environment had a very low ceiling. And so the only way to make progress was to crawl. And then places where there was a very high ceiling, then running was more efficient and it would do running. But I think that's one of the things to think about maybe in this setup is for the sub-policies to emerge, you need some richness in your environment that needs to be thought about to get a wide range of sub-policies that you might want to then adapt to new environments in the future.
So do you have any advice for someone who wants to do this and they have a new problem that they want to tackle? When should they stop or?
So let's see. I think the end-to-end training is a little easier to set up than some of the other approaches because when you end-to-end train, your objective tells you explicitly. Whereas if you say, I believe this information theoretic criterion is going to lead to HRL, which we definitely tried for a while, the problem is that even if you achieve your information theoretic criterion and you have a high score in it, you might still not get the behavior that you wanted, and then you might have to go revise your info theoretic criterion and hope that you now made a better choice. And you might have to go through that many, many times. But when you make the right choice, maybe things will just come together and beautifully work out. And that's, of course, part of the hope there. I think something like this, variance of end-to-end, maybe more layers in the hierarchy, is one natural place to look for extension. Thinking about how to introduce variety in the environment. So you can imagine neural nets generating maybe challenges for the agent. Maybe a neural net designs the shape of the environment or designs objects you need to grasp that are chosen in a way that challenge you compared to what a random distribution over objects would do. I think those are pretty good directions in terms of pushing this forward.
Okay, thanks.
Thanks, Albert.
Okay, I don't think we have time for more questions. But so now we have the Best Paper Award, and our sponsors will jump in to give it